Okay, thanks, Martin. Let me start sharing my screen. So, good. Can you guys see my screen? Yes.
Yeah.
Okay. So the first, so the first exercise that we're going to be working on this part of the workshop. Can you say it again? Nope. So the first exercise that we're going to be working on this first part of the tutorial or this part of the tutorial is calculating the vibrational frequencies of a model for H2 absorption onto a surface. I think we've done quite a lot of geometry optimization and frequency visualization in the past sections of the workshop. So why do we care about this kind of thing, or at least why did we pick this kind of model? So as I was saying, ideally, if you're trying to model something that's like a gas molecule absorbing to a surface, you would try to find the spectroscopic signatures of this kind of process and try to understand how these things relate to, you're breaking a chemical bond or strengthening a chemical bond. So that's what we're going to try to do today. Unfortunately, we don't have enough time to do, a full surface model. So our surface is going to be replaced by a simple copper plus atom, and we're trying to model the absorption of H2 into that surface. So this is how we're going to do it. Maybe I think it's better if I do it this way. So this is how we're going to try to do it in Q-Chem, in IQMO. I think you have access to XYZ geometry, initial geometry for this system. You're going to set up a calculation to optimize this geometry, just like we did in the previous section, using the omega 97x-d functional in this basis. Just be careful that you have to input this basis manually, change the charge and multiplicity, and then add a second job to calculate the frequencies. And you can add the second job by clicking on this green arrow or using the tools that Peter explained in the previous tutorial. So, something's wrong, but that's okay. So what are we going to be looking at in the exercise? We're going to try to identify from the frequency calculation what are the which one is the H stretch mode. So there are a few ways. One way is that you look at the coordinates from the output and see which ones correspond to the two hydrogen atoms moving or stretching. Or the other one, and you're going to see later that this is the mode. Or you can, just go to IQMO and visualize each one of the modes individually and see which one corresponds to a stretching. So once we do that, I think the main questions are, can we compare this with a free H2 stretching mode at equilibrium distance and see if we can find any, as I said, signatures of the H2 bond being weakened by the, adsorption to this copper atom. So I think this is what we're going to do in the first exercise. I'm going to now let Juan share his screen and walk you through the second exercise.
For the second exercise, we will be employing TDDFT to calculate the excited states of thiophene. And I believe you've seen enough information about how to construct molecules in IQMO. In this case, you are provided with a XYZ file, which contains the geometry. You simply drop it into IQMO, and you should see the molecule pop up. And to set up the calculation, you go through the usual procedure of clicking calculation and then opening up the Q-Chem setup window. At this point, we're going to need to manually modify the rem variable section because there's going to be some options that are not available in the standard tools here on the left. So for this exercise, we would be using omega B97X-D, which is a good functional for excited states, the OCP6X0 basis sets. This three rem variables that have the cis word in it talk about the excited states, the excited state calculation itself. So in this case, we're going to be asking for 20 excited states. We're just going to be looking for the singlets and not for the triplets. And lastly, these two rem variables tell you, ask Q-Chem to provide you with the files that contain information about the orbitals. So once you've verified that the rem variables are correct, that there's no spelling mistakes, you go ahead and click submit, give the job a name, and click OK. This calculation should take roughly 40 seconds once it starts running. And once you receive the results, you'll be asked if you want to copy the results from the server. You click yes. You need to create a new empty folder, and you click open, and then the files will be dumped into that folder. A yellow star should appear once the job succeeds. And now we're going to move on to the spectral analysis. So on the results that were generated in the left panel, you would be clicking on excited states, which would open up this window that has some information about them. It has the calculated energies, the oscillator strengths. In this case, since we only ask for singlets, we would be seeing just S-squared values of 0 that correspond to singlets. And then you would see a graphical representation of this information. So what you would want to do then is perhaps broaden the stick spectra with either Gaussians or Lorentzians, and go and compare to experiment. So it turns out that when people were doing this, and the analysis of this molecule thiophene in 1999, the spectra that they observed featured this small peak right here at roughly 5.5 EVs, and another big peak at around 7 EVs. In their experiment, they were showing that this corresponds to A1 and B1 pi to pi star transitions in both the features, perhaps involving different pi orbitals. And we can see that the calculated spectrum matches the experiments fairly well. You do need to shift a little bit, which is due to both the basis set that we've used and due to inherent errors in TDDFT. Lastly, what you want to do is take a look at the natural transition orbitals, or NTOs. This tells you something about the character itself of the excited states. So if you drop down the surfaces menu and click on the very first option that you have, which is TDA singlet state 1, you should see this window open up that it asks you to add a surface. For the moment, we're not going to modify anything, but just click calculate, at which point you should see the orbital being plotted. So you'll see that for each excited state, we would be able to plot what is called the Hantu and the Luntu. And this is another word that people give for these things is the whole state. I think is a little counterintuitive, but whole state roughly means where the electron is coming from. And in the very first excited state, it is coming from a pi orbital of A2 symmetry in the C2V point group. And then we're going to be putting it onto the Luntu or particle state, which roughly means where the electron lands. And it is a orbital of pi star character and B1 symmetry in the C2V point group. Yep, so at that point, we have a computed spectrum that we can compare to experiment. And not only that, we can interpret it by visualizing it. So at this point, I'm done, and I'll let Kate take over.
Great, thank you so much to all three of the speakers for this session, to Martin and you guys as well. So I will, there is one question, I'm not sure who would like to answer it, by Guima in the chat, just saying, how can we make a surface of a metal or other materials in IQ mole? So